Okay, so we just finished in the last video talking about applications of an exponential growth situation and how to use a basic exponential equation to solve problems related to growth. In this video, we're basically going to go through that same process, but we're going to talk about decay problems instead. So the beginning part of this video, the first half, there will definitely be some overlap with the last video. But there's some key differences when we talk about decay. And so that's really what we're going to emphasize in this video are what things did we talk about in the last video and how are they different in this situation when we're switching from growth in the last video to decay in this video. And then we will do a problem together where we work through a decay scenario and solve a problem. All right. So with that said, taking a look at our learning objectives, I somewhat abbreviated these because it's basically the exact same learning objectives we had before. Know the three parts of the basic exponential function, particularly as it applies to decay, and then be able to solve decay problems. Okay. Now, when we did this before, I'm looking back at the notes from the last video, we had those learning objectives, and we spent a fair amount of time developing this idea that a growth function is going to grow as you move from left to right. And that sort of implies that as time goes by, big things are getting bigger. And so we talked about the number in front was the initial value. Your base was going to be something bigger than 1. And that your exponent will frequently, but not always, represent time. And it'll be, there won't be a negative sign in the exponent. Okay. Now, most of that applies also to decay, with the exception of some of those little details. So as we talk about decay, our graph flips, right? So we start with big numbers, but they're getting smaller. It's still asymptotic. We're never going to quite hit the x-axis, but it's getting smaller. We're still going to have this same basic format to our problem, which is going to turn into the same basic equation. But here's the first thing that's different. The equation could potentially look two different ways. So the first key difference that I want to make sure that we're good with is a review about why the equation could potentially look two different ways. So if you think back to the video that I made on the properties of exponential equations, the way that you tell whether or not a function is decay is based on looking at the exponent and the base together. So in one scenario, and this is probably the more common, well, in our class, this will be the more common. I think in certain applications, maybe in some science classes and stuff, this might not be more common. But in this our class, it'll probably be more common. We will tend to have a scenario where the exponent does not have a negative sign, but the b value is less than 1. So that's the first situation that could happen. So I'm going to call this number 1, type number 1, situation number 1, and type number 2, situation number 2. So what could happen here is you could have b be a number that's less than 1. So it could be like 1/2, 1/4, 0.9 even, whatever. But x, the exponent, does not have a negative sign. Okay, so if I were to turn that into an example, perhaps I say something like b is 2/3 and x does not have a negative sign. A can be any number. It doesn't matter, positive, negative, bigger than 1, smaller than 1, that doesn't matter. Okay, so maybe something like that. And this would represent decay because of the fact that I've got no negative sign and my number's less than 1. So that's one scenario that you'll see. And like I say, as far as our class is concerned, that's probably the more common, but it's not always that situation. Situation number 2 is we keep b bigger than 1. We allow b to be bigger 1, but we put a negative sign in the exponent. Okay, so this has no negative sign. This does have a negative sign. Okay, so you might think of it as looking like that. So what this part becomes is a number that's bigger than 1, but the exponent has a negative sign. Again, A can be any number. It doesn't matter. Positive, negative, bigger than 1, smaller than 1. That doesn't matter. And then that is still a decay equation. Okay, that would still be a decay equation. All right. So actually, you know, if you're writing in pencil, I hope I'm going to make a little change because I think that I would feel better about this if it was written a little differently. I'm not going to make that a 4/3 like I had there. I'm going to change that and make it a 3 halves. Okay, so I think we all agree that 3 halves is a number bigger than 1, right? That's 1.5. 3 halves is a number bigger than 1. And the reason I want to make that little change, this is some math that we're not necessarily going to go into. It's a little bit beyond the scope of our class. But if you are really good with your rules of exponents, you could give some thought to this, and I bet you can explain why this is true. But here's the statement I want to make. This equation and this equation are exactly equivalent to each other, okay? These will always give the same answer. In fact, if you don't believe me, you could test it. Pick any number you want, plug it in for x in this equation, pick any number you want, plug it in for x in this equation, type them both in your calculator, they will always give you the same answer, always. Okay, so these are both the exact same decay function, they just look a little bit different. Okay, so that is really the only difference from the previous video on growth to this video. A still represents the initial value. And when we look at graphs, that will still be our y-intercept, okay? But the only thing that's really different is the b and the exponent. So with that said, let's take a look at an example and work through it together. Now, I do need to apologize in advance. This example is a little bit long, but I intentionally tried to find an example that, first of all, was not about time. Okay, so I wanted to make sure we had an example that was not dealing with time so we could talk about that. And then second of all, I just had to find something that had all the different information and sort of made sense what was going on. So I know that's kind of a long problem. You should pause the video right now so you can get that copied down, and then we'll talk about it. All right, so hopefully you have this copied, all right? Remember, the first step is to understand the problem, ignoring the numbers and the equations and formulas, just understanding the big idea of what's going on, because if we understand the big idea, that will help us to fit the pieces together. All right, so what this says is a person goes higher in elevation, right? Elevation, we know that means as you go up from, technically from sea level, right? So even just going up in an elevator in a tall building is technically going up in elevation. Certainly on an airplane, as your airplane flies higher and higher and higher, you're going up in elevation. This particular thing talks about climbing Mount Everest. So the higher you go, you're going up in elevation, okay? Now, the higher you go, the less atmospheric pressure you feel. So notice how this is getting bigger, but this is getting smaller. So that's a decay situation. As I go up, the pressure is going down. If we think about this graph right here, I could say that on this graph right here, my elevation, my altitude, how high I am above sea level, that's what's going up. And then my pressure, how much I feel as I go up, my pressure is going down. Okay, so that's the kind of scenario that we're dealing with right here. Okay, then they give us some information. At sea level, a person experiences approximately 101 kilopascals. Okay, now if you're not a big science person, you don't know what a kilopascal is, that doesn't even matter. Okay, that's just the units that we're using. Okay, now the atmospheric pressure drops approximately 12% every kilometer of elevation. So let's think about, again, I'm getting too focused on the numbers. Let's forget about the numbers for a second. At sea level, there's a certain amount of pressure I feel. The atmospheric pressure drops a certain amount for every kilometer I go up, okay? So again, that's describing the way things are changing. So this has something to do with my change, all right? we want to write a model. So we specifically have to write an equation that relates pressure to elevation. So pressure to elevation, that means my pressure is my y-axis, my dependent variable. That's what my function is finding, related to elevation. So elevation is my x-axis, my independent variable. That's what I'm plugging in. And then we're going to use that model to predict how much pressure we will feel at the top of Mount Everest, and they give us a number for that. All right, so that's what the problem is asking. Now we want to start organizing our data. The first thing I'm going to do, because since we did this already in the last video, it's not a surprise anymore to us. The first thing I'm going to do is just write down my basic equation. So I know my equation is going to look something like this. Okay, something like this. That's what my equation is going to look like. And now I'm going to find the numbers in my problem to see what I can figure out. So I've got this 101 kilopascals. Okay, so that's a number that I'm going to use. 101 kilopascals. Okay, I've got this 12%. So this 12%. And then I've got this approximately 8.8 kilometers. Okay, 8.8 kilometers. Okay, so let's think about how these three things might fit in. And this is where understanding the story is helpful and important to me. Notice the way the story works. What's happening is the person is going up as the person goes higher. The person is going up. So as I think about the change, what's happening is I'm going up and up and up and up. So if I want to try and figure out an initial value, the initial value is something that I experience when I'm at the bottom, right? So if going up is what's happening in the problem, then initially I'm not up. Initially, I'm at the bottom. So if I think about my three numbers, which one of those three numbers corresponds to being at the bottom of, well, in this case, I guess, of Mount Everest? Well, being at the bottom is when I'm down by the ocean, right? The ocean is certainly much lower than the top of Mount Everest. And since this is the pressure at the bottom, this must be my initial value. So that's the first thing I need to recognize, is that the A value is going to be 101. Okay, now the next thing is I know that B deals with the way things are changing. And so obviously the 12% tells me about the way things are changing. It's going down, it drops 12%. So just like on the last problem, what we did was we said 1 plus the percentage as we went up. This time we're going to say 1 minus our percentage as we go down. So 1 minus 0.12, I believe, is going to be 0.88. Yes, it is, 0.88. So that's my change. That's what I'm going to plug in for B. So the function that I'm working with, now, actually pause right there for a second. Now that I have that information, I have to decide, do I need X to be positive or do I need X to be negative? So if we go back and we look at our two scenarios, X is negative when B is bigger than 1. Is my B value bigger than 1? No, it's not. My B value is smaller than 1. So since my B value is smaller than 1, I need to leave my X without a negative sign. So my X is just simply going to be an X, okay? Now here's the thing, to be honest, right? If I were to make it negative and then plug 8.8 into it and type it into my calculator, what will actually happen is I'll end up with a pressure that's bigger than 101. And since we know the pressure is supposed to be going down, it's supposed to be dropping, it's supposed to be getting less, if I got an answer bigger than 101, I would know something was wrong. But okay, now I've got my model. So I've answered this first part, write a model. That's done. I've got it. And I'm going to plug in my altitude at the top of Mount Everest to figure out how much pressure my mountain climber will feel when he or she gets to the summit. So for this, I would just type that right into my calculator, order of operations and all that business. So 0.88 raised to the 8.8, that's a little tricky, lots of 8s going on there. That's the answer I get. And if I multiply that by 101, then the pressure that this mountain climber feels is only 32. I'm just going to say 32.8, I think is what I'm going to do there. 32.8 kilopascals. Right? And so that would be, oh, you can't see that. Sorry about that. That would be my answer, 32.8 kilopascals. All right, so that takes care of it for this video. Thanks for watching and have a good one.